SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering, and in today's class we shall discuss about the first law of thermodynamics applied to the control volume system. And if we try to recall that in the last class we have established the mathematical expression of first law for a control mass system undergoing any general process. So, now question is that having established the expression of first law for a control mass system which is applicable to any processes, then why do we need to go for the expression of the first law which is valid for the control volume system. So, you know that we have studied fluid mechanics, and in this course, as I told you in the last class, we shall be discussing a few systems. To be precise, thermal systems like power system, refrigeration system, system which are used to operate the internal combustion engines, and those are known as mechanical systems. So, in all these systems we shall learn slowly that there is a working substance. Not only the working substance is fluid, rather there will be a continuous flow of the working substance. So, in all these systems, net transport of energy either in terms of heat or work is done through the transport of a working substance which is fluid. And in fluid mechanics, you know that we have learned the transport equations are generally expressed from a control volume approach rather than a control mass approach. So, if we try to write the that since all the processes involving a flow of a fluid, transport equations are generally expressed from a control volume perspective rather than the control mass system. Here also the underlying transport of heat and work, I would say the underlying transport of energy is or can be studied conveniently for a system in which fluid flow is involved from a control volume perspective, and that is why the first law of thermodynamics can also be expressed. Rather, we should see today how can we express the first law of thermodynamics from a control volume perspective. So, just for the recapitulation, whatever we have discussed in the last class, the first law of thermodynamics right. So, for the control for a control mass system, we could write the expression is like this. Here one important assumption is that the changes in kinetic energy and potential energy are neglected. Okay. So, this is the assumption and it is because of this assumption what we could write change in energy with this change in internal energy. Okay. So, this is the first law of thermodynamics for a control mass system, and this is valid when the process is any general process. It is not necessary that the process has to be a cyclic process. Okay. So, now today as I was talking about that for the flow system, and that is what we should discuss today. For the flow system, I mean thermal systems in which flow of a fluid is involved. In fact, we shall be discussing all those systems in our subsequent classes, and in these systems, flow systems, if you would like to study the transport of energy, I mean transport of energy by heat and work, it is better, rather it would be convenient to study that particular aspect if we can express the first law of thermodynamics from a control volume perspective. So, this is the first law of thermodynamics for the control mass system. If you would like to express this particular system from the control volume perspective, then a mathematical expression will be required. So, the mathematical transformation will be required. So, we need to have mathematical transformation of this particular equation, so that we can conveniently study the transport of energy from a control volume perspective. I am not going to discuss in detail, though you have studied that particular aspect in fluid mechanics, but you know that if you would like to express, or if you would like to change, or if you would like to write the transport equations from the control volume perspective to the control from a control volume perspective, one important equation is used, and that is known as, I mean one important theorem is used, and that is known as Reynolds transport theorem. So, the Reynolds transport theorem is used to express the transport equation from a control volume perspective. So, if we try to just recall what is Reynolds transport theorem. So, or RTT in short, that is just I am writing the expression assuming that you have studied this part in fluid mechanics course. Right. So, this is the expression, and we should write one important term, just I am marking it. Okay. And then another part is there, that is control surface, again I am marking this particular term, this. So, you can see that I am not going to discuss about this particular equation, but this is Reynolds transport equation which is used. This equation allows us to write the transport equation from the control volume perspective. So, you know that here n capital N, that is any property, right. You know that this n is essentially an abstract, it can be anything. So, it is any property, and small n that I have encircled here, I mean in the first and second term of this right hand side. So, this is property per unit mass. Small n which is encircled by this green color, which is property per unit mass. So, if we look at this particular equation, you can see that left hand side of this equation, which is time rate of change of the property, and it is as I told you, it is it can be any property of the system, while it is change of the time rate of change of property n within the system. So, the time rate of change of any property within the system can be expressed in terms of the time rate of change of the property within the control volume plus this extra term is there. So, this extra term is the rate of efflux from the control surface through which flow will takes place. So, as I told you, our objective is to express first law of thermodynamics from a control volume perspective. Why? Because all the systems that we shall study in in this course is involved with the transport of any particular fluid, that is as a working substance. So, when there is a flow of fluid, so the net transport of energy because of the transport of fluid is essentially this term. So, basically that this is time rate of change of the property within the system, which can be written in terms of the time rate of change of the property within the control volume plus the rate of the efflux of the property from the control surface, or rather from the control surfaces in which flow is there. So, it is rate of efflux of the property from the control surfaces where flow occurs. Okay. So, let me write it where flow occurs. Okay. So, this is that case. Now, as I told you, we shall try to write or express, that means this transformation equation will be used to write the first law of thermodynamics for the control volume system. So, that I mean essentially, as I told you, first law talks about, rather it is a statement of the conservation of energy. So, when there is efflux, so as I told you, for the control volume system there is efflux through the control surfaces where flow occurs. So, now when there is a flow, so mass flux is there. So, you know that, so this term essentially indicates transport of energy because of the transport of mass. In a system, in a control volume system, we may have multiple inlets and multiple exits. So, through multiple inlets there will be a flow, and again through multiple outlets there will be a flow. So, the energy transport due to the mass flow is taken care by this term. So, why I am telling you? So, essentially if you would like to write first law of thermodynamics, we also need to have the mass balance equations, because in if you would like to write first law of thermodynamics for a control volume, the energy balance that first law essentially talks about is not a balance in an isolated manner, rather the energy balance has to be coupled with the mass balance. Why? Because mass flux is there because of the flow, and the energy transport associated with this mass transport should be taken into account. So, if we try to write the mass balance using this equation, so mass balance. So, you know why we need to start with this mass balance? Because in a control volume system, when you are trying to establish the energy balance equation, this mass balance is an integral part. So, mass balance. So, when capital N equal to m and small n equal to 1, right. So, we can write dm by dt system equal to d dt of Cv rho into dV plus I am writing Cs rho into V relative this eta cap dA, right, because small n equal to 1. Okay. See, small n equal to 1, so I did not write 1 over here and 1 over here. This eta cap, this is a normal pointing outwards. So, outward normals. Outward normal. See, that. So, basically if we try to complete this equation by doing 1 or 2 steps more, what we can write that dm dt for a system. So, that this is for the system. So, this is for a system and this is for a control volume. So, essentially left hand side talks about the control mass system, right. So, in this case, so a time rate of change of any property within the system, that is control mass system, can be expressed in terms of control volume plus the efflux term. So, by definition mass is fixed for the control mass system, because this is the definition. So, this quantity is equal to 0, right. What about this quantity? This quantity, that if I try to write using different color, so this quantity is nothing but mCv. So, this is mCv, right. So, if we try to write this equation is 0 equal to dmCv dt plus what this term? This is relative velocity. This relative velocity can be written like V minus Vc. So, control volume is fixed in control volume is fixed in a reference in which velocities are described. So, this is relative velocity, which is nothing but the fluid velocity minus the velocity of the control volume, right. So, I mean it is the definition. Now, this term, if you try to recall that this is if flux from the control surface, V relative dot eta cap, if we integrate it over the control surface and assuming that the properties are remaining uniform, that means rho is remaining uniform over that particular cross section. So, here important concept is that if we integrate this term and if we assume rho is remaining constant over that particular cross section, I mean if we have multiple inlets, multiple outlets through which fluid flow is taking place. So, this is essentially this term is essentially mass flux. So, this is mass flux from the control surface. So, you know that we will be having mass flux through the inlet, we will be having mass flux through the outlet. So, if we try to write it, so this would be mass flux through the inlet plus mass flux through the outlet. So, I am writing here. So, this is I, this is E. Here I am writing inlet, I stands for inlet, E stands for exit. I am using the same notations which are followed in the textbook. So, this is mass flux rate of mass leaving from the inlet if we have multiple inlets and multiple outlets, that is why I have used this summation sign. Now, I would like to discuss this V relative dot eta cap, this is outward normal. So, if we take a control volume like this and if we have, so this is outlet and this is inlet. So, you know that V relative dot eta cap is positive for the outlet or exit, it is negative because normal is always pointing outward from the control surface. So, this unit vector outward normal, which is this is pointing outward from the control surface. So, the dot product will be negative for the inlet and it will be positive for the outlet. So, if we try to change the if we try to write it correctly, it would be positive, it would be negative. Rather, I can write it in a form that is exit minus inlet. So, this is basically mass balance equations, mass balance equation. Again I am telling E stands for exit, I stands for inlet. I have discussed about the sign convention because this V relative dot eta cap is positive for outflow and this V relative dot eta cap is negative for inflow. Okay. So, that is why that this sign we have already discussed this and we also considered that particular sign convention in this equation. So, this is the mass balance equation and summation sign is taken if we have multiple inlets and multiple exits. Okay. So, try to understand by using this equation, that is Reynolds transport theorem, we could write the mass balance from a control mass system to the control volume system. Okay. Next, we are going to discuss about the energy balance. So, energy balance, as I told you that n is abstract, it could be anything. So, basically you know that n, say it is capital E. So, that is what I am writing. Since we are trying to write the energy balance equation, and energy balance equation we will be writing from a control volume perspective. Now, we are using this Reynolds transport theorem. Now, n, as I told you, it can be used to describe any property. So, here we are writing E. Therefore, small n will be equal to small e. So, this is specific energy. So, if we try to write the Reynolds transport theorem, then we can write d dt for the system equal to d dt of control volume rho e dv plus we are writing control surface rho e v relative eta cap dA. Mind it, the small e is the specific energy, right. So, this is what we can write. Now, it is very important that what we can do further. So, this is essentially you know this left hand side gives us a clue about the change in energy within the system. So, it is essentially you know the first law of thermodynamics, and this part, I mean again if I try to write using different color. So, this part can be written. So, you know that one important assumption that I could not write over here is that I am writing properties are uniform over the respective cross sections through which flow occurs. So, this is important assumptions. This is one of this is an important assumption which is used to describe this equation. So, here we can write this is del del T of rho dV. Again I am telling, if we take that this is within the control volume. So, this is capital E C V, right. So, you know that rho dV, that is mass E, small e, I mean that may vary within the control volume, but you know that if we multiply with that mass we will be getting total energy. So, this is this this expression, this quantity can be written like this, plus I can write this expression in this form, that control surface you know rho e Vr dot eta cap dA. We shall come to this particular term later. Okay. Now, as I told you that this gives us an information about the change of energy within the system, time rate of change of energy within the system. You know, I would like to tell you one important thing in this context, that you have studied about thermodynamics, right. So, why we are calling it thermodynamics, why not thermostatics, right. So, in thermodynamics you know dynamics, the word dynamics is coming from the fact that whenever we are trying to study something, or rather whenever we are trying to describe something which is having time rate of change of any property. So, basically time rate of change of anything, I mean if you would like to study, then only the word dynamics will come into the picture. In thermodynamics also we would prefer to write sometimes the equations in the rate form, and that is why we are writing d dt with the system. So, time rate of change of energy within the system, since we are trying to write it time rate of change. So, that is why the word dynamics is coming into the picture. So, it is not a thermostatics. So, this gives us impression about the first law of thermodynamics of a control mass system. So, basically if you would like to know the time rate of change of energy within the control mass system, then I mean what we can do, I mean this is the change of energy within the system, and that is basically again I am telling that is essentially giving us a clue about the knowledge about the first law, right. So, as I told you, first law essentially talks about the energy conservation. So, it is a statement of energy conservation. So, this term, left hand side term, which is giving us the, you can clearly see that is the time rate of change of energy within the system. So, that is giving us a knowledge about the first law of thermodynamics. So, this fellow can be written from the first law which is applied to a control mass system. So, if we try to write first law applied to the control mass system, that is nothing but del cube equal to d plus delta w, right. If we again ignore the changes in kinetic and potential energy, I mean changes in kinetic and potential energies, then we can write it in this form Q, but we are writing, since we are trying to write the general, we are trying to express the general form of the first law of thermodynamics, it is better to write E. Now, see, you can see that this quantity is basically written in the time rate form. So, we also, so this is first law for a control mass system. Essentially that is the change of energy within the system. So, if we try to write in the rate form, what we can write? We can write like this, say del q and del w and d, all these quantities are written in the differential form, but we have to keep in mind that q and w, these are the path functions. So, we have written in the form of inexact differential, wherein E is the point function, because this is the property of the system, and that is why we could write in the form of a exact differential, in the form of exact differential. So, now if you would like to write these quantities in the rate form, we can write like this, delta cube by delta t as limit delta t tends to 0 equal to limit delta E by delta t tends to 0 plus limit delta w by delta t tends to 0. Again let me tell you one important thing, why we are considering delta t tends to 0, because you know that the Reynolds transport theorem, the derivation of the Reynolds transport theorem is based on important assumption is that the delta t tends to 0, that means the system and control volume are coincident. So, basically when delta t tends to 0, I mean if you try to recall the derivation of Reynolds transport theorem, if you can't recall, I would suggest you to consult with any standard fluid mechanics books. You will find that the Reynolds transport theorem is derived based on an important assumption is that delta T tends to 0, and this is considered keeping in mind that the overlapped area, that is the system and control volume will coincident. So, that is why we have written delta T tends to 0. Why? Our objective is to express the rate of change of energy from a system to the rate of change of energy to the control volume. So, basically we are trying to express the rate of change of energy from the control volume perspective, and that is why we are trying to do it. So, you know that we can write it that this is q dot equal to, this is d by dt plus w dot, right. So, if we try to write it in the next slide, so we have written q dot equal to d dt plus w dot. Hence, we can write, this is for the control mass system. So, we can write this is d dt for the system, right. So, this is d dt for the system. So, if we write it, this is for system, that means d dt for the system can be written q dot minus w dot, right. See, so whether should we write q dot minus w dot, this is for a system or for a control volume? It is essentially for a system, right. So, the quantity which we have written here, that is in the right hand side of this equation, this quantity is also applicable for the system. I mean, we have written d dt for the system. So, this is q dot minus w dot, this is also for the system, but we can write this quantity to be as applicable to be control volume as well. So, this quantity can be written, I mean this is as good as q dot minus w dot control volume. Why? Because we have taken an important assumption that delta T tends to 0. So, as delta T tends to 0, system and control volume are coincident. So, that we can write. So, if we try to look at the expression which we have written over here, that d dt system now can be written q dot minus w dot, this is C v equal to d C v dt plus rho E V r dot eta cap dA control surface. Okay. So, this is what we can write. Now, I would like to tell you, so basically you can see that starting from the first law of thermodynamics for a control mass system, we could write this expression. So, here you know that this is q dot, that is change of I can write the time rate of change of heat within the control volume minus this is time rate of change of total work within the control volume, is nothing but the time rate of change of energy within the control volume plus the rate of energy flux. So, basically rate of energy into the system and rate of energy out from the system because of the mass flux. Now, see this w dot. So, if I try to write it again using different color, since this w dot, if we write this w dot, it is having two different components, right. What are the components? You know that if we talk about a control mass system, still there will be w dot, because it is energy transport either by heat or by work. In this particular course, in fact, you have studied in thermodynamics that we talk about energy transport either by heat transfer or by work transfer. So, if we try to write this w dot, one component will be there, that is w dot C v, So, this is basically that is work done within the control volume. So, either work is added to the control volume or work is taken away from the control volume. On the top of that, one additional component will be there. Try to understand, because we are trying to study the first law of thermodynamics for a control volume system. Why? Because most of the thermal system that will be discussed in the subsequent classes, involve transport of a fluid. So, when there is a flow of fluid within this control volume, I mean we are trying to describe, then a part of work will be associated with that. Why? Because to maintain the flow in the presence of a pressure, so without pressure difference flow will not take place. You have studied in fluid mechanics. So, if you need to maintain continuous flow in the presence of a pressure, then there will be work done. So, this work done I am writing, this is flow work. So, this is the control volume work. So, basically you know that this is total work. So, this part is the work done by the control volume or work is done on the control volume. Either work is added to the control volume or work is taken away from the control volume. On the top of that, this component takes care of the intrinsic work done associated to maintain the flow in the presence of pressure. If this part work is, rather I should say energy. So, this part of energy is not there. I mean if we do not have energy associated with the transport of flow, then flow will not survive. So, basically to maintain the flow, some part of energy will be associated to that, and that is W dot flow. So, if we try to write this equation, Q dot minus W dot minus W dot flow. Okay. So, this is the left hand side. I am writing the left hand side. So, what is flow work? You know that you have studied in fluid mechanics. Say we have a channel, parallel plate channel. A very simple example I am taking, and if we need to have continuous flow, say if we have a control volume and the control volume there is one inlet and there is one outlet. So, there is a continuous flow to the control volume and there is again continuous outflow from the control volume. So, this is outflow and this is inflow and this is Cv. See, if we need to have continuous inflow and continuous outflow, some part of energy should be associated with that, otherwise it is very difficult to have, it would be difficult to maintain the flow, continuous flow. So, if we take out this small part and if we consider this part, so say this is the inflow part and I have taken here and I have tried to draw the zoomed in view. So, if we have say pressure, so continuous flow at its inlet, and if we considering pressure here is P, and it is because of this pressure the flow has advanced a distance say delta x through the channel, right. So, this is inlet channel. Now, to maintain the flow in a continuous manner, we need to have flow work or work done. So, work done to maintain the flow in the presence of pressure, because and if we assume that the cross section, the length of this particular portion is so small that the pressure is remaining almost constant. So, we can write work done to maintain the flow is equal to P. So, P into A, that is force into displacement. So, that is work done. If you would like to write per unit mass, so this is work done per unit mass equal to P A delta x. If we consider that density of the fluid is rho and that is also remaining constant in this particular cross section. So, as I told you that properties are not varying over the cross section through which flow occurs. So, basically mass would be rho into A into delta x. So, you can see this is nothing but P by rho. That is what you have studied in fluid mechanics course, that is known as flow work. So, the energy required to maintain flow in the presence of pressure is P by rho. In thermodynamics, it is convenient to write in terms of the specific volume, because the specific volume can be easily calculated from the linear interpolation from the property chart. So, this is the specific volume. So, if we try to write the equation again, Q dot minus W dot minus W dot flow. I am not writing CV because just I have omitted CV. So, basically this W dot is work done by the system or on the system. So, basically whether work is added to the system or work is taken away from the system. You know that flow is there, on the other hand that some amount of work done will be there within the control volume. Okay. So, that is nothing but dE CV dt plus rho E VR eta dot dA, right. See, we have written this is work done per unit mass, but so work done due to the mass flux which is mass flux into the system, and work done due to mass flux which is mass flux out from the system. So, this is work done per unit mass. If we can calculate the mass flux into the system and mass flux out from the system, then we can calculate total, right. So, you know that if we try to go back, that this quantity rho Vr dot eta cap dA, this is mass flux. So, this is mass flux from the control surface. So, mass flux out minus mass flux in. So, if we have control surface at the inlet and control surface at the outlet, so mass flux out minus mass flux in. Essentially what I would like to tell you is that rho Vr dot eta cap dA is the mass flux. So, we can write this quantity in this form, that control surface PV into rho V relative. So, this is V relative dot eta cap dA. We can write, if we take out this particular term to the right hand side, right. So, again if I take this particular term, so this is the total mass, so total amount of flow work due to the mass flux in and mass flux out. So, if we take this term to the right hand side, we can write this equation like this: Q dot minus W dot. So, this is work done within the control volume equal to dCV dt plus, if we take this control surface rho outside, then we can write E plus PV, E plus PV V relative. I have written it like this. So, V relative dot eta cap dA, right. So, this is straightforward. What I did, I have taken this term in the right hand side, and just I have tried to club these two terms together. So, this is E plus P v. What is this E plus P v? So, basically if we write one step further, that we can write Q dot minus W dot equal to d C v dt plus control surface rho into E plus P v into V r dot eta cap dA. What is E plus P v? E plus P v is half c square plus g z plus small u. So, this is specific energy. So, I have taken I am writing half c square plus g z plus u plus P v. You have studied in thermodynamics that if we write u plus P v, we are getting another important property, that is enthalpy. So, we can write this is H plus half c square plus g z. So, that means we can write one step further, that Q dot minus W dot equal to d C v dt plus control surface, it is written H plus half c square plus g z V relative dot eta cap dA. So, this is first law of thermodynamics, which is very important to write over here, that the first law of thermodynamics of a flow process across the control volume. So, this is first law of thermodynamics of a flow process across the control volume. So, this is the this is very important, H plus half c square plus g z. Question is, if the system is non-flow system, that is control mass system, we could write this total energy in terms of U. So, if it is a non-flow system, instead of H we can write U plus half c square plus g z, the total energy. But for the flow system, that is control volume system, where there is a flow across the control surface, the total energy is written H plus half c square plus g z. So, this is nothing but the internal energy. So, try to understand, this total part is nothing but U plus this is P v plus half c square plus g z. So, even if we do not consider the changes in kinetic and potential energies, this quantity for the flow system is nothing but the internal energy of the system plus energy required to maintain the flow in the presence of a pressure. Again I am telling, even if we do not consider the changes in kinetic and potential energies, this quantity indicates the total energy, which is nothing but the internal energy plus the energy required to maintain the flow in the presence of a pressure, right. So, this is the difference between the control mass and control volume system. So, for the control volume system, we are getting one extra term, that is enthalpy, and this is basically thermal energy for the flow system. So, this H is the thermal energy for the flow system, and U is the thermal energy for the non-flow system. So, this is what is important difference. So, you know that one important assumption is there, that properties do not I mean we will discuss again, we will go on a few steps further to describe first law of thermodynamics for the flow processes across the control volume, right. So, taking a few assumptions, we can write this expression in different forms, that part we shall discuss in the next class. So, with this I stop here today. Thank you.